Hi, I'm Seth, and in this video, I'm going to show you how to run a one-way ANOVA in R. First, for reference, on the right side of the page, I've already run an ANOVA for these three samples in Excel. I did it in a piecemeal fashion and got the F statistic 1.02 with this sample size that is not significant. I've also got the R squared right there, the effect size for the overall model. So how do we do this in R? Well, there are many different ways you could do this. For simplicity, to include as few functions as possible, I'm just going to manually input these data into a data frame. So first, I'm going to create a variable. I'm going to say score is equal to, now I'm going to use the C function for combine or concatenate, and I'm just going to list all of these scores, 4 through 6, and then I'm going to keep going 6 through 5, and just keep going in order until I have them all here, separated by commas. So okay, I think that's right. So now, once I run this code, score means this sequence, this vector of numbers. Now, I'm also going to create a list of identifiers. So group 1, group 2, and group 3. Specifically, I'm going to say repeat the words group 1. Repeat that there are 7 cases in the first group, 14 in the second, and 6 in the third. Okay, so repeat group 1 7 times. Then repeat group 2 14 times. Then repeat group 3 6 times. And then let's see what that looks like. Oops. I made a mistake right here. The 7 should be inside of the parentheses. Otherwise, what's happening is it said group 1 a single time, then it said 7, then it proceeded with the rest of the code. But I want it to say group 1 7 times. So the 7 needs to go inside of as the second argument for this rep function. Now, it does what I want. Group 1, group 1, group 1, 7 times. Then it says group 2 14 times. Then it says group 3 6 times. Now, I could just run an ANOVA immediately, but first I'm going to use it. I'm going to create a data frame just so we can visualize this and make sure it looks like we want. So I'm going to say df for data frame is equal to, you can use the data frame, data.frame function to create a data frame, and it's going to be made up of group and score. All right, so create that and then show it to us. Here we go. And this is what we expected to see. This is the same information as you can see right here, except I've got it all in 2 columns. So all the scores are in a single column, and then there's another column to the left showing what group a particular score goes with. So for group 3, we have 5, 6, 2, 2, 3, 3. And that's what we see here. Group 3, the first value is 5. We have another group 3 of 6, 2, 2, 3, and 3. So this is what we want. Okay, so to run an ANOVA, one way you could do that is just in base R using AOV for analysis of variance. And we will say, let's see, how does it want to receive this? So it wants to have the formula first, and then it wants to receive the data. So we'll say score predicted by group. So your dependent variable or outcome variable comes first, then you do the little tilde, and then you say your independent variable or your predictor variable, comma, and then specify where it should be getting the data from. Okay, so if we do this, we get, it runs everything. Let's see, the Sums of squares for the group is 4.99. That's what we got over here in Excel. The residual sums of squares are 58.64. Again, that's what we got here. So it looks like it's doing what we want. I'd like to see the F statistic though. So I'm going to nest, I'm going to use the summary function. And then I'm going to take this and put it inside of that summary function. So I want it to give me a summary. Now it is giving me the F statistic 1.02. That is the same statistic we calculated in Excel. And you can see as well the p-value. It is not significant by any conventional standard. Now, suppose you wanted to know the effect size for the model. Here we calculated it. We already know it's 0.078 or 7.8% of the variance explained. There's actually a few different ways you could do it. I mean, you could just calculate it using the information you see here. R squared is equal to the sums of squares explained by the model. So sums of squares for the group divided by the total sums of squares. So, well, let's just see. So it'd be 4.99 divided by 4.99 plus 58.64. So it's, well, let's just see what we get, 0.078 or 7.8%. What this shows is the proportion of the total sums of squares, which is the residual and that's explained by the model. What proportion of that does the model sums of squares account for? And in this case, it's about 8%. Now, if you can't be bothered to write a formula like that, we could, let's see, there's many ways we could do this. Let's use our statics. This is one that I use sometimes, this package. We can do ANOVA test. And let's see, what does it want? Okay, so it wants it the other way around. It wants to get the data first and then the formula. Okay, so df, comma, score predicted by group. Okay, so you're seeing some of the same information. You can see an F statistic of 1.02, the p-value from before, and then also GES, that's our effect size, 0.078, same as we calculated before. Now, because this F statistic is not significant, we would typically stop here. But let's imagine that the data were a little bit different. I'm going to make it so that, that the F statistic will be significant. So I'm going to take this third group and I'm going to increase each score by 10. So this becomes 15, 16, 12, 12, 13, 13. And yes, this F statistic is significant, 76.96. All right, let's go ahead and replicate that in R. What did I do? I added 10 to each score in the third group. All right, that looks like it worked. And yeah, now our F statistic is 76.96. P-value is smaller than any conventional threshold or most unconventional thresholds even. And our overall effect size for the model has jumped to 87%. So almost 87% of the variability in these scores is explained by group membership. So in this case, we would probably want to do some sort of follow-up tests. Not always the best choice, but one way that you can do follow-up tests is just pairwise comparisons, where we simply compare each group to every other group. Just, t-tests comparing each pair of samples. So let's just do that real quick. We can use also from our statics pairwise _t _test. Okay, and then we're going to take the same information that we used above and just plug it in again. So do pairwise t-tests in this data frame with score by group. Okay, when we do that, actually, I'm going to go full screen to show this part. When we do that, you can see each of the pairwise comparisons. So like this first line compares the mean of group 1 to the mean of group 2. You can see the sample sizes in each group. the p-value. So this first, in this first case, it's not significant, which, by the way, we kind of knew that was going to happen because there's no new information here that we didn't see in that first ANOVA that wasn't significant. The only change has been in group 3. And accordingly, you can see when comparing group 1 to 3 and group 2 to 3, the p-values are significant. Okay. You can tweak some things, like I think this uses the home correction by default. You could say p.adjust.method, and then say if you wanted to, for example, do a Bonferroni correction, you could do that. And your raw p-value comes out right here, and then p-adjust is your adjusted one. And in this case, we've run 3 tests, 3 post-hoc tests, so this p-value is simply tripled with the Bonferroni correction, and same for this one. Well, they're all tripled actually, but this one tops out at 1. Okay, or maybe you don't like the Bonferroni, maybe you like the Benjamin Hochberg, or however you pronounce it. You could use BH. In fact, if you want to know all your options, you can say help for a particular function. Then we could come down and find, here we go, p adjust method, and you can find all the different kinds of adjustments it can do. Okay, and there are other ways that you can tweak this to, for example, control whether variances are assumed to be equal and all that fun t-test stuff. But we're going to keep going. So let's see. Timeout. While watching that playback, I realized I glossed over a few important details which could cause you to get different results than you expect to. So one thing I should say about this pairwise t-test function is I wouldn't just leave out this component if you don't want to make any adjustment. If you don't want to adjust for multiple comparisons, set it equal to none, because by default it is going to use some. I think it uses the home correction. Additionally, by default it uses this argument. It uses pool.sd equals true, which means it's going to pool the standard deviations. If you don't want that, you should specify that it's false. So for example, if you wanted to run 3 t-tests with no corrections, just independent samples t-tests, treating the variances as though they were true, or as though they were equal, we would say pool sd equals false, comma, bar for variance dot equal equals true. Now, if you run this, the results will be what you would get if you ran 3 independent samples t-tests with no corrections and assuming the variances are equal. But a lot of times you are going to want to apply some kind of correction, even if you do assume equal variances. But that's a topic for a different video. Okay, back to the original video. What we should talk more about these effect sizes. In fact, maybe I should have done that from the outset, but let's do it now. So I'm going to need the tidyverse library for the way that I want to do this. And I'm going to say, I'm going to take my data frame and I'm going to group by group membership. So group by group. And then I'm going to use summarize. And I'm going to create a column where we have the mean of, how would I do that? Oh, the mean of score. And then a column called SD, which gives us the standard deviation of the score column. And let's do N for the length of score, because I want it to count. I think this will do what I want. Yes. Okay. So here we have some descriptives, like you can see for each group, the sample size, as well as the mean and standard deviation for each group. So these, the differences between these means are some of the effects we should really care about. You know, we spend 95% of our time talking about significance testing, trying to see, is the effect anything other than literally zero. But really, the main story is about the differences, the raw and standardized effects, the differences between the means that is more interesting. Like in this case, group 1 and group 2 have very similar means. Group 3 is much higher. Okay, so we can also that could allow us to get some raw effects, but we might want standardized effects such as Cohen's D. We can do this using R statics as well, I believe. What is it? Cohen's underscore D. And then we'll just input the same information as before. Okay. And there you go. For the score column, comparing group 1 and group 2, you get the effect size, and this has been standardized. So this is the difference between those means expressed in standard deviation units. So there you go. That's one way to run an ANOVA in R, including pairwise comparisons and calculating effect size, like this standardized effect size. All right, that's it for today. If you have questions or comments, don't hesitate to reach out. See you next time.